this video, we will consider a simplified roller coaster as shown in the diagram here. We're going to assume that the lift mechanism causes the coaster to creep over the top of the hill with a very small speed, 1.5 meters per second. Then the coaster is going to accelerate down the hill under the influence of gravity. We're given that the coaster's mass is 300 kilograms. We'd like to know what the speed of the coaster would be when it hits the bottom of the hill. This is a very challenging problem if you use a force diagram approach, but we're not going to do that here, because the purpose of this video is to make your life easier using energy conservation. I'm going to quickly walk through how you would solve this problem using a force diagram approach, only to show how difficult it is. You'll see by comparison how easy the energy approach is. It really will make your life easier. If I wanted to use a force diagram approach, I would of course need to first start with a force diagram. It would look something like this. I would need to tilt the force diagram so that the x-axis is along the surface of the ramp. Fgx, the x component of gravity, ends up being the unbalanced force on the coaster, and using some trigonometry, we can find the magnitude of that unbalanced force. It happens to be 2,408 newtons. Once we know the net force and the mass of the object, we can calculate the acceleration using Newton's second law rearranged. We find that the acceleration is just over 8 meters per second. Our next step would be to determine how far it actually moves down the ramp. We weren't given that in the problem. We were given the height of the coaster and an angle. So we do some trigonometry to figure out that the delta x along the ramp surface is 42.7 meters. And then we can find the final velocity in a couple of different ways. I could use the position equation and the quadratic formula to determine that it would take 3.08 seconds for the coaster to reach the bottom of the ramp. Once I know that time and the acceleration from a previous step, and add in that little bit of initial velocity that it started with, we find that the coaster would be moving 26.2 meters per second at the bottom of the hill. We could also use the v-squared equation to solve that in one step. Both methods give the same answer, 26.2 meters per second. I didn't go through those steps because I really wanted to demonstrate them in detail. I just wanted to explain how we get to the answer using a force diagram approach. Keep that number in mind, 26.2 meters per second. We'll use an energy approach to solve this problem in a much more straightforward way, and it really should make your life easier. So let's look at how we would solve this problem using an energy approach. I like energy pie charts to help organize your thinking. For the energy pie chart at the top, and again, we would want to think of the roller coaster as gaining some energy as the lift mechanism does work on it as it rises up the hill. Once it goes over the crest of the hill, there's going to be a transfer of energy between kinetic energy and gravitational potential energy. At the top of the hill, there's only going to be a little sliver of kinetic energy because the cart is moving quite slow. I do want to account for it even though it's small. So I'll make a small pie piece to represent the kinetic energy of the coaster. The rest of the pie is gravitational potential energy. When the coaster goes down the hill, that kinetic energy wedge is going to get bigger and bigger. The gravitational potential energy wedge is going to get smaller and smaller. If we consider the bottom of the hill height 0, then the entire energy pie chart is in the form of kinetic energy. Using the concept that energy would be conserved, we can say that the energy at the top, and that would be the total energy at the top, should equal the energy at the bottom. At the top of the hill, we have two forms of energy, kinetic energy and gravitational potential energy. The formula for kinetic energy is 1/2 mv squared. And the formula for gravitational potential energy is mgh. At the bottom of the hill, we only have kinetic energy. Again, that formula is 1/2 mv squared. Note that this velocity will be different. If you need to differentiate those two velocities in your mind, you could use subscripts to specify that this is the velocity at the top of the hill, vt, and this is the velocity at the bottom of the hill, vb. At this point, you could go ahead and start plugging in numbers. We know the mass of the coaster, we know the speed as it comes over the top, we know the value of g, and we know the height of the hill. We know all of the terms here, so we could calculate a number. On the right-hand side of the equation, again, we know the mass of the cart, but we don't know the final velocity. That's what we're solving for. One useful tip on problems that involve just kinetic energy and gravitational potential energy is that the mass of the object shows up in every term. Here, it was a 300 kilogram coaster. We could certainly plug that in each term, but we can make our lives a little bit easier by canceling that term. Imagine dividing all 3 terms by m. We could cancel it out. This is a great tip in problems where you're not given the mass of the object. It turns out that the mass of the object doesn't matter in finding the velocity at the bottom of the hill. That's because gravity is driving this process. And as we know, all objects accelerate at the same rate under the influence of gravity. At this point, you could plug in numbers and solve, or you could use algebra to rearrange the equation. Again, we're trying to solve for v subscript b. The algebra is going to look like this. I would multiply both sides of the equation times 2 to cancel the 1/2. That means the entire left-hand side of the equation needs to be multiplied by 2. That cancels everything over here except VB squared. I want to take the square root of that side of the equation and the square root of this side of the equation. Plugging in numbers, it's going to look like this. This is VT, the velocity of the coaster as it comes over the top of the hill. That was given as 1.5 meters per second. Don't forget that that term is squared. And then we have the value of g, 9.8 meters per second squared, times the height, and that would be the height of the object at the top of the hill. We're using 35 meters for that value. That whole quantity, again, is multiplied by 2, and it's going to tell us the velocity at the bottom of the hill. At this point, you just need to be really careful in plugging the values into your calculator correctly. And don't forget, this whole quantity gets multiplied by 2 before you take the square root of the entire quantity. You'll also notice that if you carry through units, we have meters squared over seconds squared for this term. And this term also comes out to be meters squared because we have m times m over seconds squared. When you take the square root of meters squared over seconds squared, you get meters per second, which is the velocity unit that we expect. If you plug in those values, you'll find that the velocity at the bottom of the hill is 26.2 meters per second. That's the exact answer that we found when we used that much more complex force diagram approach that required many, many steps to solve for the velocity at the bottom of the hill. So hopefully that makes your life easier. We could take this problem a step further and illustrate how energy conservation can solve problems that would be nearly impossible to do with a force diagram approach. The cool thing about energy conservation is you could continue to track the energy totals for the roller coaster as it proceeds through the rest of the track. Maybe there's a loop next. In the next video, I'll demonstrate how to find the speed of the coaster as it goes through the top of the loop, reaching a height of 23 meters. If you have any questions about this video, please post them in the comments. Thanks for watching.